Hello and welcome to my video. Having recently watched most of Usagi Electric's series on building a vacuum tube computer, I've been inspired. I haven't messed around with transistors or valves at all in a very long time because you get sort of wound up working with microcontrollers and you just sort of lose that grassroots thing. So I've decided I'm going to start playing around with transistors a little bit more and looking for a project. The obvious project would be a 1-bit computer such as their valve computer, but that would be a little bit like, I don't know, following in the footsteps of an Explorer in a air-conditioned 4-wheel drive. It just wouldn't be the same. So looking for ideas and being a fan of the Mr. Matt and Mr. Che YouTube channel, I started thinking about whether it would be possible to simulate an elevator controller using transistors. Looking around YouTube doesn't look like it's been done, and looking at Matt's videos, he's only really encountered one situation where a controller has actually been transistorized, and it was pretty messed up condition. So it seems to be something that hasn't really been done, so perfect. I'm going to give that a try. Before we start, first we'll need to make some decisions about how the circuits are going to work. First decision I need to make is whether I use bipolar or field effect transistors. Field effect transistors don't apply a load to the source and drain junction. The gate is completely isolated. So this makes them very, very well suited to logic because it means that you can have a much larger fan out between the transistors. The problem I've got is most of my experience has been with bipolar, so that's what I'm going to stick with for this. Next decision is whether I want to use open collector or totem pole outputs. With totem pole outputs, you have a transistor that will be driving the output high, or a transistor will be driving the output low. But if you have a number of totem pole outputs on the same input, the potential is there for one of the devices to be driven high and one to be driven low simultaneously. The result is the entire power supply goes through that resistor. Not necessarily a problem, however, if you have a number of devices that are all high and one device pulls it low, the parallel resistance will mean a lot of current flowing through that transistor. The result of that could be pretty serious damage. So I will be going with open collector for most of what I'm using. In that situation, a transistor's base and emitter junction will drive the collector emitter junction low, and for a high output, an open on the base will just simply leave the collector floating, and this external resistor will pull it high. So multiple gates sharing that same bus will all be pulling the current for that one resistor, and that will mean that it doesn't matter how many devices are pulling it low, the current will only get lower, not higher. So that's what I will be going with. Next decision will be whether to use TTL or DTL logic. With TTL, you have basically all transistors, whereas with DTL, you have a lot of the legwork being done by resistors, and the transistors are basically just there as buffers. So let's now have a look, see how hard it is to actually create this logic. So I'm going to simulate it using Falstad. So there's our two diodes, a transistor. Now here I'm going to put a pull-up resistor. And of course the collector, so the emitter will go to ground. Then we hook up our inputs. and of course we've got our output. So let's see what that looks like. Our output is on when our inputs are off. I turn either input on, it goes low. Turn both on, it goes low. So what we've got here is a NOR gate. So to make it an OR gate, just simply add another separate transistor stage to it. Now the output is low, both inputs are low. Turn an input high, the output goes high. Turn the other input high, the output goes high. Of course, if they're both high, the output's still high. So that's our OR gate. And of course also we had the NOR gate. So the next one to look at will be the AND gate. Now when you look at these diodes, you can only use those to OR, you can't AND with that. So this is where we need to get a little bit creative. When we look at the truth table for an OR gate and an AND gate, we look at the OR gate, we see a situation here where if any of the inputs are on, the output will be on. So that's an OR gate. But with an AND gate, we can also look at it the same way. We can say that if any of the inputs are off, the output will also be off. That's an OR gate, but there's inverters in the process. So this is basically DeMorgans Theorem, where you can convert ANDs, ORs, NANDs, NORs from one gate type to another just by the placement of inverters around them. It's very useful if you're running out of a particular gate type in a circuit. Also, it can make it a lot simpler because, well, you can have inverters cancelling each other out and things like that. You can save a lot of electronics there. So let's see what that looks like. To start with, let's delete these diodes and replace them with diodes going in the opposite direction. Now these switches will drive them low, or if the switches are on, they'll reverse bias the diodes and they'll do nothing. But for the low condition to work, there needs to be a power source. So put another pull-up resistor in. So let's see what we get. Both inputs are off, the output's off. That's good. One input's on, output's still off, that's good. Other input, that's good. Both inputs, nothing. And that's because that wasn't connected. So now both inputs are on, the output's on. Turn either input off, the output's off. So that's our AND gate. And of course, if we remove this transistor, it becomes a NAND gate. So from here, we have basically covered all of the main building blocks: OR gates, NOR gates, AND gates, NAND gates, and inverters. So next, we'll be moving on to slightly more complicated circuits. We're going to start with a set-reset flip-flop circuit. This involves either two NAND gates or two NOR gates. It's great that they're NANDs or NORs because that means one less transistor each. NAND gates actually work a bit better, so that's what I'm going to use. But the inputs are active low, whereas for the NOR gate version it's active high. They're actually also flipped. So let's take a look at the circuit. So there is the basic design there for a NAND based. Here we have the first, here we have the second, and you can see set goes into the first, reset goes into the second, output comes off the first, and then the inputs and outputs are fed back. So let's try making it. So I'm going to start with, actually move those along, our 2 diodes, and then another 2 diodes. Now we're going to add the transistors. And then pull up resistors. Connect the emitters to negative. Then we hook up our inputs. Loop the outputs back to the inputs. And that should be it. So that's set, reset. Perfect. Now, because they're active low, we want to put a transistor in here and here just to invert the signal. Now I also want, for safety, just to add some 1K resistors. Put those on the bases, just in case these get connected straight to supply. It means the current being fed in will be limited. So let's give it a try. Okay. That seems to be working. It's set. Turn the output on. Then reset, send that high, turns the output off. Okay, so that's the basic circuit for a SR flip-flop. 4 transistors, 4 diodes, 4 resistors, plus an extra 2. That should be it for that. The circuit shown here represents the floor selector, the navigation part of it. These contacts represent each floor, and if an elevator is sitting at a particular floor, the contact for that floor will be open. These are the call switches, which would go to the SR flip-flop circuits that are used for the call buttons. And then any of these inputs going high will tell it that the lift needs to go to a particular floor. So if I hit the circuit for 1, you can see the signal is coming through this diode to level 1, has routed down to the level 1 output. Now these two outputs for the top and bottom are there only to tell it whether there are calls waiting above or below. They're not actually what control the motor. So if I hit 4 as well, you can see both are on. These diodes are there to prevent backflow, as you can see from here. We don't want the signal from level 1 travelling back to level 2's transistor. So as you can see from this, that's the basic logic behind the navigation. There is a separate logic behind the actual direction control of the motor. That logic is based on determining whether there are calls waiting above or below, and it will travel in one direction picking up calls until there are none left. Then it'll reverse and go in the opposite direction picking up calls until there are none left. It will keep doing that until there are none left at all. So that's the basic logic behind that. So the next thing we'd need to look at would be the actual motor control aspect of it. This is the motor control logic. The floor selector here, we have the elevator position switches and the actual call switches. These will connect to obviously the SR flip-flop circuits for the call switches. So these can both be on at the same time if there are calls in both directions, but the motor should never be on at the same time for both directions. So we put the lift in the middle position, and then we turn a call on at the very top level. So you can see here, tops come on, and again, up direction has been selected. So now let's select at the bottom as well. So now we've got top and bottom, but still only top. So if the elevator now moves up, continues to move up, when it finally services the top call, it will now change over to the bottom direction control, and the lift will continue in the opposite direction. This will then happen until it reaches the bottom, and then it serves the last call. If I have a call selected above and the elevator happens to move beyond it, see the direction will reverse. Reversing while it's operating obviously is going to be a bad thing, but there's a lot more logic that happens around the stopping and the clearing of the calls. So the clearing of the calls will only ever happen during a stop state, which means a change of direction will only ever happen whilst the motor is not running. So as bad as it seems to be changing over so easily, in fact it would never actually happen.